Centre, stroke SSTL, stroke whatever hat he wants to wear at the time, who's going to give us a really interesting talk on the ESEO payload. Thank you, Chris.
Thanks very much, Dave. So yeah, today what I'll be talking to you about is where we sort of left off from at the last conference, where we'd actually done a demo of our ESEO payload, the transponder itself, and the beacon that typically comes out of the Funky satellites developed by AMSAT-UK. So it's not just me that does all this stuff. There are the usual suspects: David Bowman, G0MRF, and Graham Sherville, G3VZV, as well as perhaps most of the team, perhaps in this kind of front row of people. I kind of allocate them into that kind of same sort of band of people. And we've been working on this for quite a while now. And it originally started back in the late 90s, where where ESA wanted to build up a couple of missions, ESEO, which is the Earth orbiting student satellite, and one called ESMO, which is a student version of the same things to go around the lunar system. And in particular, they were looking at universities that could work with ESA Education Office to build new things, develop new parts, and then fly them and qualify them as part of this ESA program. And sort of the latest information you can find kind of goes back a bit further than that, but the more recent ones are in about 2008, and you can kind of check out all the kind of ESA pages on that. Now, this is a microsatellite, so it's about 60-ish kind of kilos, and we essentially have a small box that goes into the side of this panel here, and includes a VHF transmitter, an L-band uplink, and then it has a microprocessor and power supply board. We also have on the top an antenna at the top, a small dipole up there, and then we have a patch antenna that kind of sits on this bottom plate here. So that's kind of the sort of thing that you have on there, and there are all sorts of other payloads, and a good example of that would be one from Cranfield University on there as well. They've got a drag sail, and there are cameras and other pieces that other universities have been developing. So in the group that I've been working with Graham and David, kind of started in 2014, where I'd been able to help rope in my students into building and helping design a lot of this equipment. And we started kind of slow. We obviously started with dev boards, some things, and GNU radio parts, to then begin to sort of test what we wanted to do and what we wanted to transmit. So we wanted to then sort of move some of the stuff that we'd kind of had and seen and working on computers for sound card modems and other sort of modems, and start to develop them and put them on the chip. And so I had two guys, Eduardo and Victor, who were from Brazil, doing a Science Without Borders program, which essentially they were doing part of their modules in their MSc where we could swap between the university. And that means then that I could grab them myself, so that I could then allow them to use their techniques and develop their skills in developing the sort of digital pieces. And what they were doing is kind of analysing the signals. I wanted them to sort of take in some standard signals, whether it be FSK, AFSK, BPSK, and start to analyse them, and just to get to grips with what sort of handling we would need and sampling we would need to use on board the actual satellite. So the first thing was kind of say, well, could we identify where we've got our noughts and ones? Could we put in proper markers of where we expect any of the timing to actually physically sit? And then can we window and average and actually make sort of hard and soft decisions on what is happening with the receiver? So of course, when we're uplinking, we're doing that, there might be high Doppler on that, and so some of these things may drift in and out. So some of you that have used SDRs and software modems might have used Direwolf or Multimon, any of these sort of open source sort of utilities, and we essentially took that source code and we essentially bastardized it so that we can then use it on board this particular chip. We then went on and kind of improved it as well. So if you're finding that Direwolf or Multimon isn't really working for you and it drops packets and things like that, you need to have an averaging window, because it kind of loses its phase on some of the signals. The next year after that, I was then being able to take two other students, Ben and Ben, to then start to then develop and build the PCB. So the next thing we've done is we've developed some signals of what we needed. We needed then to sort of build the PCBs and develop them, and this is part of their third year sort of undergraduate course. And in fact now Ben is now working on his PhD, and actually so is the other Ben, this one in physics and this one in our electronic engineering department. And so we've been able to then sort of build it up piece by piece. But each time I do it, we kind of realise what sort of requirements this this thing, the unit needs to have, and actually how different it was to perhaps some of the previous FunCube designs. One of the things that we had to do is, as well as having our downlink and our uplink and do transponder services for AMSAT, was to be able to then interface as well to ESA's main bus, which is over control area network CAN, and in particular CAN open. So this is the sort of thing that most modern cars use now. So the latest Priuses, the sort of latest cars, they use CAN open typically. And we need to then have our own sort of internal pieces as well. So the telemetry comes from I2C monitoring and power switches, so that we can then operate this this unit and transmit the actual sort of FunCube signal. On top of that, we're all doing this kind of all on one chip. And so we're using an automotive part made by Atmel. And what we wanted to do as well, and I guess because I'm a sadist of some sort, is I decided then that the students need to start developing real-time operating systems and developing on top of those systems. So this is something that people take for granted anyway, that you have in your set-top boxes, and you have an operating system that manages everything for you, and it manages all those timings. And in particular, the pieces that are interesting is the digital to analog converter, so the actual sending out of the spectrum that goes to the modulator, but also then an interrupt-driven ADC as well. So this analog to digital converter here, we're going to be sending in signals, whether or not it's voice or whether or not it's physical commands. They're going to come in asynchronously, and we don't know when they're going to come in. So it's going to need to then be able to do all of that stuff all at the same time, and then essentially slice up the processor usage, okay, on the chip. We also then need to meet a whole series of ESA software standards as well, which was very, very demanding of certainly some of my students who, when confronted with best part of 200 requirements, went, what the hell, okay. But what I wanted to do is sort of focus on sort of the building and some of the SDR activities. The next victim, let's call him a victim, that came along into our web for ESEO was Pete Bartram and Andre, and both of these two guys worked mainly on the software and the building of what was the engineering model that you might have seen from the last AMSAT Colloquium sort of conference parts down in Guildford. And this is kind of what the unit looks like. Inside of here, we've got the L-band, the VHF boards, and then we have kind of one single sort of integrated CCT board, which I'll show you in a moment. But we were able to sort of do that, do the first sort of tests, and then immediately after that we were then able to then sort of deliver that out in Italy. But there are some pieces that I kind of wanted to talk to you about, because they are kind of some tricks that we did when you're going and doing SDR and doing digital work that I think, as the takeaway, you might find really useful. So when we are transmitting and we're going sort of actually out of a raw modulator, one of the things we typically have to do is we filter. And we do that obviously not just in hardware, but we can also do that in software too. And the classic approach that we use to do that is on BPSK systems, so we use a raised root cosine filter, and we can develop different filters for doing different data rates and different sizes. And there are lots of tools that are out there that will give you all of these different coefficients and different ways of doing it. The typical way that you do it is through convolution, so it's a sort of addition and multiplication of different signals together that you then shift along kind of in a window. And the way that if you do that, you end up with, look, a huge number of coefficients, and these are just constants that you then have to keep into memory. You have to then use them and develop with them. And when you sort of do that and you kind of map out all of the things that you need to do, well, you kind of then get to a point where if you're going to be doing 130 multiplications and accumulations that have got to happen all the time at a known sampling rate, then you kind of then work out how many floating points or how many flops, how many types of computational power you're going to physically need to be able to do that. And so we were looking at 5.1 megaflops of power. That's what we needed to do if we were going to do that in just that classic way. Now the way that you can get around that is you can sort of pre-calculate them and store them. So this was kind of using 35% of our processor, just filtering, just outputting the filter, not doing any encoding, not doing anything else, just filtering. And the way that we could reduce that was by pushing everything into a lookup table. So you kind of pre-analyze, you sort of work out what needs to happen, and it then pushed it into flash memory. And because we have lots and lots of flash memory, it's usually much bigger than the RAM you have on the chip. This is very, very tiny. We can then reduce down this sort of overhead here. And it means then this can drop from 35 down to something like 4%. Okay? Just from knowing where you need to kind of push in and out your parts of your design. This is the sort of test signal that we would typically work with. So you would see the typical 0.7 second tone that kind of goes on from here, and then the rest of it is then BPSK telemetry. So we've been able to then prove from this that the filtering was right, that everything was doing as it should be. The next step was then going, well, actually we want to go faster. So we wanted to develop faster systems, so we went to go from 1K2 to 4K8. On the uplink, for signal processing, we had a kind of similar problem. We used Multimon, the C library, to sort of get ourselves started. And from testing, we were looking at sampling rates. Okay, when you're trying to look at a signal coming in, a waveform coming in, whether it be this, you obviously need to be sampling 2.2 times the Nyquist rate. Okay, so you can recover successfully the signal. Now, if we needed to do that, okay, we essentially were getting different success rates. So if you were sending a 1K2 signal up, you really need to be sampling at 4K8 or something higher than that. So you've oversampled it, so it means you can definitely recover your signal. And because we were using an operating system, we could then actually use a lot of tools to visualize what was happening inside the processor. In particular, we were then using Google's XUnit test framework. This is a really easy C++ language that means then that we could generate sort of test sequences and test tones in a very, very simple way. So if you're going to be doing validation test and unit tests of your software, this Google framework just kind of runs out of the box and is a really kind of straightforward way to do it. And what we were noticing is inside our processor, this is the kind of the usage here, 30% really was being managed. And then what we were doing is we were hitting peaks. So when we needed to then send stuff out onto the DAC to downlink information, we would hit peaks of 100%. So this is like a massive no-no, okay, period. Usually in processing on most satellite systems, if it's even vaguely close to 50, like I'm panicking. Okay? It shouldn't be anywhere near that. There should always be spare cycles in your computer to handle that real-time element. Okay? So if this thing isn't transmitting or sending the right data out to the DAC at the right times, then all those bit sequences are all wrong. Okay? You're not matching the timing, things and these waves start to all go out of phase, and everything goes a bit wibbly. Okay? And that's what we were kind of seeing. So when we were uplinking to it, what we were doing is matching it again. So we were doing 1K2, so we might sample much higher at 4K something, but it consumed 95% of the processor. What the hell? And what we decided to do is kind of drop that again, but then our success rate went down because, of course, we're creating ambiguity in our sampling. Drop down the processing, but of course that meant that we weren't getting a successful amount in. And at 11 kilohertz, we were really oversampling. We got 99% success, but really it was just using all of our processor kind of all the time. And the trick that we used from that is that everything in this particular library was in floating point operation. And floating point operation to embedded computers, ones that you typically find simple PIC microcontrollers, Arduinos, any of those sort of pieces, a floating point operation isn't just one clock cycle. Okay? The way that it does a floating point operation is by shifting and adding, if you're doing multiplication, or it does shifting around of exponential functions, and it breaks things up. So instead of it being in one clock cycle, it usually takes around 20. Okay? On a 32-bit processor, it's probably a minimum of 15 to 20. So what we ended up doing is we moved it all from floating point to just fixed point integers. As soon as we did that and shifted everything down, everything dropped right the way down, and everything was looking nice, kind of at around this level. Okay? That was just from changing the data type on the exact C code that you were typing in the processor. So knowing and looking at sampling, okay, those are some of the tricks that we use. On our downlink, making sure that if you need to use filters and tables, pre-allocate everything and figure everything out beforehand. And remember what your actual physical processor is doing. If you don't need floating point precision, then don't use it. Okay? So those are some of the tricks that we can use. The packet format that we have that comes down should look familiar to some of you that are familiar with Funcube. What we have is we have real-time telemetry that comes down, as well as whole orbit data ones, and those are what you'll see from Funcube 1, the UCube 2 Funcube Payload, as well as the QP50 ones and Naive as well. So there's lots of those that are out there, and they kind of look like this, and they sort of come down in a 5-second piece where you've got a tone at the beginning, data and data. Okay. Now what we'd said is obviously we wanted to then do that quicker, because this is a software-defined radio, we can then go faster. Okay, we can use a bit more and modulate a bit more. And so what we've got is an extra couple of different modes that allows us to transmit things down much, much faster. Okay, so the tone will no longer have this nice sort of beep tone that I'll show you in a second, but it actually has a very, very quick one. So instead of getting one of these down in 5 seconds, this comes down in about 1.3 or something like that, just over a second. We've also got an extra mode in there so that ESA, if they wanted to, could then downlink some further data. So if they had any problems with their main bus, we needed to actually put in more software to then take over control of it, be a CAN master, request 2 kilobyte chunks from people that we would then downlink in this 4K8 mode. So already we're doing kind of a bit more than we kind of needed to. If it wasn't for this operating system that can handle I2C, the CAN, the DACs, the ADCs, we'd have had to really make some interesting kind of software and do a lot more testing. But what we've been able to do by using the operating system was just test everything in isolation, put things in and out, and begin to test them individually. It means then that you can get more than one person to work on the same thing. Okay, so if you have got plethoras of students or lots of amateurs, you can all pick something. Okay, you can all go and work on just one part of that and really own it. Okay, which is something that's really important. So what's inside? Okay, so when we're transmitting, this is essentially a screenshot of what each of our threads are doing. So all of these individual tasks that we get our operating system to do happen essentially in threads. And these threads, really, we can see kind of how often they get serviced. So most of the time, we're really doing downlink operations. We're sending stuff in and out. We might be doing some small CAN pieces. We might be, getting a packet coming in from our uplink. And we might be transmitting or communicating with the rest of the satellite bus. But we're doing this all at the same time. We've only got one processor, and what we do is we interleave everything together, and we let the operating system decide how to handle those real-time requirements. All we do is we tell it, your DAC must be able to get this data at this time and at this rate, and it's up to that to then figure it out. We let the scheduler handle that. Okay, so that's the real power of using an operating system. Inside, it still follows the same FunCube forward error correction format that was developed by Phil Kahn and the AO40 system, which goes through read, Solomon, scrambles, convolution coding, and interleaving. Now, for this particular satellite, that might be particularly overkill, because this was really designed for a satellite that may have unknown attitude, but we hope, touch wood, okay, that the attitude will be much more stable on this one. Okay, but at least then there's no further than ground station and ground segment software that we would have needed to have changed on the dashboard. So we did more testing. We literally got everything. There's our 4K8 signal. Actually, if I can turn on the sound, let's see if I have a jack. It doesn't look like the sound's really on that.
Yeah, yes, if nothing's changed, then it'll just.
But you can kind of see how quick it is. I've got sound on the other ones. We'll leave that plugged in.
If nothing's changed, then it'll just.
Yeah.
That's a smoke alarm, isn't it?
You can kind of see it's going much, much quicker. Oh, was that Duncan?
That's a smoke alarm, isn't it?
Sounds like a smoke alarm. Okay. So everyone's used to getting quite a 5-second bit of data and then quite a nice tone that people can hear for their radios and their handies that they can use. If you hear that, it's mean we're going at 4K8. We're going much, much faster coming down on the downlink. What we then had to do is we then had to deliver it out in Forlì in Italy, and so the whole team went out, and we've been able to then take Pete Bartram, he's our MSc student, out with us, which is obviously a great experience for him as a student. Sort of gets him a bit more invited out into the field as well. And we were able to integrate it then with the other flat-sat parts as well. So we have our AMSAT payload here, we have all of our test equipment and our ground station parts over there, and then this then operated then as the rest of the satellite. So they had emulators and other subsystems that could then work kind of in parallel, or we can then test all of the features on the satellite. What was really good is that actually we were testing the things, and the main thing we were worried about was our interface over CAN. So that's the main sort of link that we had, the data bus to the main satellite. And the most complex mode we had was obviously to pull data off of something else, bring it over and start to spit it out. And it worked first time. And we're like, oh, okay then, I guess we'll go home now. So we spent a little bit more time just looking, testing other pieces, but we were like, well, we're done here. So that unit has stayed out in Italy, and the Italian team from CITEL and ESEO have been kind of testing that. So inside that, after we delivered the EM, we then need to deliver the PFM, so this is the proto-flight model. And what essentially had on this board was essentially a power segment, as well as then the processing digital side. So we kind of have two planes when we split up this PCB. And this was done by one of the German students we had on our ASC program, Jonas Hostiger. And the voltage that comes in is 28 volts from the main satellite bus. It gets then converted down into 9, 6, and 3v3, which then goes onto the digital section. Over here, we've then got our Atmel processor, and we then connect that to an I2C part that then goes out and then measures everything. So we can get current and voltage, all those regular things that you see on the FunCube system of really what's happening on the satellite down on here, except there's an extra couple of interfaces for CAN and some more interfaces over here that goes out for our BPSK output and our uplinked FM system as well. But then this was developed purely by Jonas, and it moved us then nicely on for ESA's requirements, what we call then our flight readiness review and our test readiness review. And our flight readiness review is a meeting where we all get together to agree the timelines, what's going to happen and when. But we also then have a test readiness review. So when we finally build the unit and we put each of the individual pieces together, ESA then have to review all of your test procedures. And what they do is they essentially go, what are you going to do for vibe? How do you know it works? How do we validate it? And how do you meet this bazillion and one requirements that we typically have that come out of ESA? So we had to generate actually a lot of documentation that they had to review to kind of go through and start to begin before we even done any testing. They have to agree all the procedures and everything all in advance. So with that happening, we sort of moved very, very quickly on because we were starting to sort of run out of time and actually running out of good students that I wanted to have that works on the project. And we moved on then into the first thing that we typically do in an environmental test campaign, EVT campaign, which is vibration. So we have a vibration facility at the Space Centre in Guildford. What we have is we have a vibration plate, and it kind of shakes back and forth using kilowatts of energy to be able to then generate the certain forces that are meant to be representative of what you would see on the launcher. Okay, so the idea of this is then you're de-risking that unit inside there. So if you've got anything in there that's going to shake apart or go to pieces, okay, that is the point when it's going to happen. Okay, and essentially when you sort of do these tests, they sound like motorcycles. They sound horrible. They sound like engines of things revving up about, I don't know, 80, 90 dBs, and you're just there going, trying to not then pray that your unit is going to burst into flames / into a billion pieces. For ESA, we had to cover everything in dust sheets as well. They wanted to make sure that everything was as clean as possible to prevent any small molecules or pieces of dust or pieces of anything from getting inside the unit. And this is kind of the only vaguely flattering picture I have of Jonas, and so apologies to Jonas on any of the live streams if you're watching. I haven't got any pictures of you, not from the front anyway, and if I do, you kind of got your eyes closed or something. So that's you, that's a good one. And he was essentially taking a lot of photos for us that we could then use to then give to ESA to show what we'd done in our test reports. After we'd kind of done that and passed our vibration test, everything was working still, we then move on to thermal vacuum. Thermal vacuum is again sort of another sort of test. So as soon as you've gone through your rocket stage, you've come off the rocket, you're of course in the vacuum of low Earth orbit. And what this does is it tries to then represent what we do inside there. And we did that at Rao Labs at Harwell, and many, many thanks to them. They did that completely free for us. That was wonderful of them. And this is kind of me with the unit kind of carried in, and this is sort of the chamber that we were using. Now, when you kind of get into these clean rooms, these are optical clean rooms, and instead of just having just a jacket, a beard net, and a hat and some gloves, you need to have all of that, then plus like another mask thing, more boots, more hats. They don't want anything to get on anything, because if you even get the smallest specks on any of their optics, it's all ruined. You've got to start again, lots of money. So even if you forget to take in the smallest cable, okay, you've got to take it all off again, then you've got to go out, and you've lost minimum of about half an hour, okay, just to get in and out of that stuff. Inside there, it starts to be very cold because you're wearing about 8 layers of stuff. It gets very, very hot quickly. So if you can, don't stay in there because you get dehydrated as well. It's very dry inside these clean rooms. This was a class 1000 clean room, which means that it has essentially an allowable 1000 particulates per cubic foot inside it. So at the moment, we're probably in this room, probably millions right now, millions of particulates and things per sort of cubic foot. Inside there, they have a requirement for 1000, so it has filtration in it. Much more comfortable outside, where we could then set up our ground station and do all the tests from. You'll probably notice the typical sort of dashboards that you see, and then I use my laptop and I developed some tools here that then essentially generated the audio that went out to an Alinco radio that we could then test and communicate to and from the clean room. So we were really right next to it, and essentially there was like sirens going on, and it's like you're in a factory, like in a corner of a factory, with no real light anywhere. It's just artificial light. So we did that for about 3 days, okay, which I couldn't get a student to do because obviously health and safety, that would be very unreasonable. So obviously I had to typically do most of that. And what we did is we actually have to test it with 4 cycles. And the reason why we're testing this is obviously we're trying to do accelerated kind of aging of the unit. What you can notice is we've got these weird little bumps here at the tops and the bottoms where we turn things kind of on and off. And the reason why we would turn things on and off at those sort of points was to really test the aging of the system, and then we do a comparison. So we look at all the telemetry when it's at +70, we do the same when it's at -20, and we then go through those extra cycles, and we then see whether or not we have any deviation. If you start to have some deviation, then there's obviously things you might want to investigate. Why would they deviate as things are getting hot and cold? So it's nice because you can kind of see these dips where the unit's kind of heating itself up as it's kind of going sort of into test. And then we sort of come out, and then it's obviously then a very nervous drive back home to make sure everything goes back in and then works. And of course, it did. So we were all very, very fortunate there. So what's different on this? Duncan, like I say, is one of the masterminds behind the FunCube dashboard. And what we were doing is we'd get back, we'd look at the signal, and we could then test things. What you can see here is we've got telemetry on here where you've got then the transponder power being received, and we were testing the command as well. And we could do that in different notches, so you can see where we're testing different powers. So what we would do is we would use signal generators as well to then plumb in and out sort of different powers. And we can get down to about minus 107-ish dBs of sensitivity, certainly on the command and the transponder. Now, on the transponder itself, we have 2 different modes that we can operate. Autonomous mode, what we call A and B. And autonomous mode A will be dependent on whether or not the satellite is in sunlight or not. So I'm going to look at the guys at the back here, but if it's in sunlight, then what we would hope it actually does is it then has transponder. It can be potentially active if it gets a 67 Hz CT-CSS tone. And in autonomous mode B, what it does is it just looks at the CT-CSS tone. If it doesn't, it just is always transmitting BPSK telemetry. But as soon as it gets that tone come in, the transponder's active, and then that is in operational, and it has a timeout for 20 seconds. Okay, so we've got a couple of modes there that allow us to autonomously switch between doing telemetry modes and transponder modes as well. When we got back, we started to notice we had some, on long-term tests, we'd seen this kind of weird issue here, where we would notice that we would have weird current consumptions, where the current would just drop, you know, for big periods of time. And we're going, I've seen that before. I'm not sure what's happening here. And we were racking our brains as to what it was. Is this an actual component failure? Because when you build this thing, you actually put lots of glue on it, we can formal coat it. This is a unit that you can't really change or break apart. And we couldn't figure it out. We'd spent much time. I can't remember how long we were looking at this. A few weeks, maybe, I don't know. It could be. It was all a blur. We couldn't remember. We were trying to figure out what it was until it came to me when I was kind of out running. And so, yeah, please all go out running, by the way, because that stuff happens. Whereby the operating system, it manages things in actual real time. It manages physical time. And the actual tones and the actual transmissions of the segments are not exactly 5 seconds. So what happens is when it takes its sampling, the operating system kind of decides to move something along, because it doesn't need to sample. It doesn't have a big requirement for when you do your sampling, provided it's once every 5 seconds. So what happens is that it kind of drifts around, and that when it gets to this point, this is that 0.7 seconds tone, that 0.67 seconds tone. And during that tone phase, actually, we are physically drawing less current. We have physically got less forward power. And so that is what that is. And that actually works out to be, if you were to take that whole thing there, that is our 5 second tone. That is about 0.6 seconds worth of physical time. So all of that kind of concluded. We figured it all out. And then we were kind of figuring out whether or not should we try and get rid of it, or is it just safer to leave it as it is? Because this is actually valid telemetry. This is the minimum that we're going to be drawing when we've got that tone. And this is our maximum that we then end. So it's left in. So you'll see that feature come through as well on the telemetry. So here's essentially what it looks like on the dashboard and it operating. So you can kind of see, again, we would have the standard sort of funky signal coming in, and we can see what mode is it all in. More importantly, the other thing that you can do on here is it actually collects data as well from the actual satellite bus itself. So we don't just get our own telemetry, we actually kind of leech off their data as well. Okay, and we want to know what's happening to their attitude, to their subsystems, what is happening with their power switches, what have they got running on right now, and you'll be able to go in there and use the dashboard to then see exactly those things. We'll also be able to know our satellite GPS position as well, so we'll hopefully be able to plot that, and we'll also know our attitude rates as well. So we'll be able to learn much more, as being this kind of parasite communicating and down and leeching actually some of the further information that comes from this ESA spacecraft. Here we've then got our funky messages as well, so like I say, it still keeps in with all of the stuff that you've seen before. This is what 4K8 sounds like. Hopefully that works. Sounds a bit weird for those that are used to the funky signal, but it's just much quicker. Okay. But at least people then know kind of what to expect to see and what to come down on the satellite. So at the moment we're in the middle of finalising our test documents and being able to deliver hopefully to ESA pretty soon. And really though, there's a lot of conclusions that can kind of come from what we've been done so far in ESEO. We've had 4 sets of SARI students that have gone through now. All of them have been either inspired or have gone on to do more things to do with space, okay? Super important that we do that. Next thing, good tools really pay off. Being able to use something like Google's XUnit testing or this real-time operating system, Percepio, sort of visualizer, means that you can physically then see what is happening on your chip, okay? Those are really good tools because sometimes it's very hard to debug what is happening, especially when your system becomes more and more complicated. We use an automotive part in here that interfaces to everything, and where you can, just obviously use best practice. So don't use floating points when you don't have to. If you can load stuff into Flash, chuck it all into Flash. Okay, and do all your pre-allocations and all your analysis beforehand. There is a Payload demo available, but there are some things that perhaps haven't worked so well. University calendars. We go from roughly an October to a June-ish sort of time, and of course there are some blank months there, and they don't always fit with long duration kind of programs. So we have to train new students as they come in, we have to figure out what they do. Some are good, some are not so good, and you kind of roll the dice with that. AMSAT team as well been able to motivate us locally, so defining all those things and helping them. And this is really key to promote a safe space to ask. So when people are working with new things and students are working with new people that maybe are in that kind of professional project working environment, they need to be able to ask. They need to be able to know, how do I do this? I'm not sure about this. And this has got to be a safe space for them to do those things. This is what's been really good about the CubeSat community. It's a place for them to do those things so that when they work on the bigger satellites, they don't go wrong. And obviously the ongoing exposure that we have, certainly in the group that I work in onboard data handling, has been really, really great, and it's obviously strengthened everything that we do. So that's kind of where we are. We're almost in at the final stages of here, and hopefully next time we talk, I'll just be able to say, we delivered it, that was it, now we're just waiting for launch, and we'll be able to copy kind of what perhaps Peter has done. But that's kind of what's happened since last year. The engineering model to the flight model, hopefully some tips there on how you might do it yourself. But obviously thanks to all of these main guys that have been working on it, as well as all the students. And with that, I'd like to finish my talk.
Thank you, Chris. Thank you. Certainly from a personal point of view, I've been involved with this as well, because I've been part of the FunCube team for a while, and Chris keeps kicking me to do my bit of the work as well.
He mentioned that. You heard him. That was not me.
I'm responsible for the FunCube data warehouse, and ESEO will be one of the feeders for that. Any questions?
Thanks for an interesting insight. For the flight model, do you use COTS components or flight qualified?
Yes. So for this particular one, we're using COTS. Low Earth orbit is actually pretty benign. The typical sort of radiation dose-wise that you're seeing is about 2 kilorads per year. I've found that most components go easy to 20K, unless you've got real doped parts. The only pieces that you really worry about are things that have borium in them. So things like your regulators, PAs, they tend to go a bit really quicker, but they last 5 years, no problem.
Okay, and what sort of lifetime are you looking for the?
ESA one, well, a minimum of a year is, I think, what they specified, but I don't see any reason why this wouldn't go on for much longer.
Okay, thanks a lot.
Oh.
There's a question from the back over there. If you can
Yeah,
speak
hi.
up, please.
3 of them, good. Let's go through them.
Which microcontroller are you using and how many bits?
Which?
Microcontroller.
So we're using an AT32 processor, AC3C, which is an automotive part. It has dual CAN interfaces, I2C, a bunch of UARTs, 44 pins. We run that at 60 megahertz.
Does it have step locking?
You can have it in step lock if you wanted to. Depends on. No, we didn't. I mean, so this has actually already been used on another Indian mission that I'm aware of, and we're quite used to qualifying and looking at automotive parts in Surrey. So we obviously have made a business in it. So that was 2 questions. What's the third?
Well, 1.5.
Okay.
So for the FC5, like the telemetry framing,
Oh yeah.
the encapsulate data, is that your own encoding?
Oh, so yeah, so the encoding still is encoded in the typical AO40 format. So if I just quickly go back to slides where I talk about encoding. So this AO40 format is still being used to encode each of those packets. So whatever we get from the ESA bus, so if ESA say, go to that code, get something from AF address, bring 2 kilobytes in, we don't care what it is, we will still encode it.
Okay. So
Yeah.
those are still on ECSS data?
It's, to me, it's data. I actually don't care. Yeah, because this isn't ECSS formatted,
Okay.
arguably. Yeah.
And the final one, are you going to be using any of the software or hardware as open source or?
I don't know. Certainly the ground segment, certainly the ground control stuff is all on Python. The RTOS stuff, I don't know. No one's really ever asked me before. Yeah, I guess we'll have to think about it.
We've got a couple of minutes to set more questions.
Any other ones? Phil?
Question from the stream, how long will it fly before the orbit?
Well, it depends on the orbit. The orbit, I'm looking at Graham here. We have no, the launch keeps changing, or keeps.
25 years from end of mission.
There you go. So there's a quite rather bland answer from the floor. Yeah, the answer was it will last less than 25 years as per negotiated guidelines between all NATO nations have signed up to. No.
I think one last question if there is any.
Going once. If not, I'll be around. Thank you very much.
That's it. Thank you very much, Chris. And it's now time.